Welcome back. Unit 5, Stoichiometry. What is stoichiometry? Stoichiometry is the quantitative study of reactants and products in a chemical reaction. It can also be defined as the chemical recipe necessary to combine substance to make new substance. So you're thinking it like if you are baking maybe bread, you know that you need how much salt, how much sugar, how much flour, how many eggs, how much milk. So stoichiometry is just the recipe of making or formulating certain substances. So stoichiometry is the quantitative study of reactants and products in a chemical reaction. So here's an analogy. So consider making sandwiches, and in each sandwich I would like to have 2 pieces of bread, which are these ones, and a slice of tomato, as you can see, and 4 slices of tomato, then 2 pieces of chicken, like that, and a piece of lettuce, and a piece of 2 pieces of chicken. So this is the equation. So you'll be saying 2 bread, 4 tomatoes, 2 pieces of chicken, then 1 piece of lettuce. So they combine to form a sandwich. So this is to form one sandwich. So remember, when you say stoichiometry is the quantitative study of reactants and products in a chemical reaction. So in the case that you say, but what if I want to make 5 sandwiches for some friends? How much of each element would I need? So it means you already have the reaction to form one sandwich. So it means you just have to multiply it by 5 so that you can get 5 sandwiches. So basically that's how it is. So it means you need times 5 of each ingredient in order to make 5 sandwiches. So that's basically what stoichiometry is looking at. So let's see, for one sandwich, we have already, is this one. Then you just multiply it by 5, as you can see here. So here 5, 2 times 5 is 10, 4 times 5 is 20, 2 times 5 is 10, 1 times 5 is 5, 1 times 5, then 5 sandwiches. So that's basically, so here you are just using an analogy so that when you are actually talking about the atoms and elements involved, you'll be knowing that that's what basically we are talking about. So I hope this example helped you to understand. Let's move on. So what you should expect. In a chemical equation, reactants are written at the left and products are written to the right. Here is supposed to be to the right. It was a typo error. To the right. So basically these are the products and these are the reactants. So reactants, and this side products. So this is the standard. Reactant on the left and product on the right. So this is how we should do it. So we are given the reactants and how much of the products can be formed. So this is an example. A and B. Okay, let me just remove this so that you can see. 2A plus 2B forms 3C. So they say given 20 grams of A and sufficient B, how many grams of C will be formed? So basically, what we are talking about here is like B is unlimited, but A is limited. So what it basically means is the amount of C that will be formed is determined by the amount of A we have. In this case, we have what? 20 grams. So when you're doing stoichiometry, that's what basically we are calculating. So sometimes we'll be saying, I want a certain amount of C, so how much products, how much reactants do I need to have? So basically that's how it works. So let's check the next slide. Excuse me for that. Avogadro's number, the number of particles in one mole is equal to the number of atoms in exactly 12 grams of carbon-12. This number of particles is called the Avogadro's number. Remember, moles, we are saying moles is it's represented by these particles. 6.022 times 10 to the power 23. That is the Avogadro's number. So the equation says 1 mole of an element, of an atom, it has got this number of particles. So they are represented by Avogadro's number. So if it's 2 moles, it means it will be 2 times 6.002 times 10 to the power 23. So when you use your calculator, you will find the final answer. So 2 moles, it will be 2 times this number of particles. So the Avogadro's number can be used to convert moles and the number of particles in a symbol shown below. So in this case, we are going to look at it in this way. So example, convert the number of moles and the number of atoms. This is an example. And a sample of titanium has got 8.98 times 10 to the power 25 titanium atoms. What amount of titanium in moles does this represent? So basically, we already know that you are asked to calculate the amount of moles in a given sample of metal. So you are given the number of atoms, which are these ones. You already know. So using your formula, 1 mole is equals to this one, to create a conversion factor that converts from units of the moles. So basically, it's more like a proportion. To say 1 mole is equals to 6.22 times 10 to the power 23. So 8.98 times 10 to the power 25, it will give us more moles. So it means we put this one on top, this one divided by this one to get the number of if you convert properly, you're supposed to get 149 moles. So basically, some questions will come. Either they will ask you to find the moles, like for example this one, because they've given you the particles. Sometimes they give you the moles and say, can you find the number of particles? So you just have to use this formula. So it's a very simple example. Is your answer reasonable? The symbol contains more than Avogadro's numbers of atoms and therefore more than 1 mole of titanium atoms. So thank you for that. I think it's simply clear. If you have any questions, you can put them in the comments or use the email on our right. Molar mass. So molar mass is the mass in grams of 1 mole of a substance. Thus, 1 mole of an element has a mass equal to its atomic weight in atomic mass unit. E.g., 1 mole of carbon is what 12 grams. So if you go to your periodic table, you can see it's written 12.6. So 12, that is what we are referring to as the atomic. So this represents that 1 mole has got 12 grams. So if you go to a different atom, the number of moles, the number of grams in a mole, you take it from this number. So for in that case, we can move on to the third point. Just as Avogadro's number can be used to convert between moles and the number of particles in a sample, molar mass can be used to convert between moles and mass of a sample, as shown below. So this is an example: convert mass and moles of an element. So what amount of oxygen in moles does 124 grams of oxygen represent? So you are asked to calculate amount of moles of oxygen in a sample, and you are given the mass, which is 124 grams. So use the molar mass. So if you go to periodic table, oxygen is 16, 8, something like this. So this number on top, that's what we are looking at. So it means 1 mole has got 16 grams. To create a conversion factor that converts mass to the amount of moles of oxygen. So basically it's the same proportion. If we are saying 1 mole has got 16, okay, sorry for that, has got 16 grams. So 128, 124, why am I always saying 128? How much we know that there will be more. So that's how we reach here. So when you simplify this, you find out that in 124 grams of oxygen, there are 7.75 moles. So notice that the units of grams cancel each other. So this is what they are referring to here. They cancel each other, leaving the answer in moles. Also know that the molar mass number is 4 significant figures, one more than the number of figures in the given data. So the significant figures, we have already discussed about them. So basically, that's what you should also take note when they're asking you the questions. They normally state how many significant figures you should use. Is your answer reasonable? The mass of oxygen in the sample is greater than the molar mass of the oxygen, so there is more than 1 mole. So this is just another way to check, to say if 1 mole is 16 grams, so 124 grams you must get more. So it makes sense because our answer has got more than 1 mole. So in other words, what we are saying, the greater the mass, the more moles you have, which is the same as saying the more moles you have, the more mass you have. So basically, this is how you convert. So what you need to know before solving stoichiometry problems, you need to know the molar ratio, you need to know the molar masses, and also you need to know balancing and interpreting equations. Then you need to know the conversions between grams and moles, because the equations, stoichiometry equations like the one we did, 2a plus 2b is equals to 3. See, the one we did previously, these are done in moles. So if you are given grams, it means you have to convert them to moles. So this type of reaction is called mass-mass problems. That's just something to note. Steps involving solving mass-mass stoichiometry problems. So first, you need to balance the equation correctly so that you can formulate important and accurate relationships between the reactants and the products. Using the molar mass of the given substance, convert the mass to to moles. Then construct a molar proportion, like 2 molar ratios sets equal to each other. So using that one that we already did, so it means, let's say you're comparing A and C. So you know that A, you need 2 moles to form 3. So this is what they mean by molar ratios. So, and for B you can also do it, B and C, so it will be 2:3. So for A and B, it's 1:1, because 2, it just simplifies to 1:1. So these are what they mean when they talk about ratios. So let's move on. So using the molar mass of the unknown substance, convert the moles just calculated to mass. So basically, both when you are doing the calculations, remember the equations, they only work when you are using moles. So you have to convert everything that you are given into moles. Once you get your answer in mole, but they want the answer in grams, then you just use the conversions. So it will be clearer when we are doing examples. So most of the examples, we shall do them on our website for comprehensive understanding. So mole ratios. A mole ratio converts moles of one product in a balance equation into moles of another. So I've already demonstrated it, like to say 1:1, 2:2, when you're comparing two atoms or a product or compounds in a chemical equation. So an example: reaction between magnesium and oxygen to form magnesium oxide. These are fireworks. So magnesium and oxygen, they combine to form magnesium. So the molar ratios is 2:1:1. Notice we are taking the moles. Here it's 1, and here, as you can see. So the other thing, remember, for you to take the mole ratios, you need to make sure that your equation is balanced. So in this side on the left, you can see there are 2 magnesium, and this side there are 2 magnesium. Remember, this 2, it's multiplying everything here like this. So this side is 2 magnesium, this side is 2 magnesium and 2 oxygens. And here 2 times 1, 2 oxygen. So it's a balanced equation. So this is what we mean by mole ratios. So practice problems. So nitrogen reacts with hydrogen to form ammonium according to this equation. Write the mole ratios for nitrogen and oxygen. So nitrogen to oxygen, this is the first set, then this one. You can try that one out. Then for the second equation, a can of butane lighter fluid contains 1.2 moles of butane. So butane, this is the formula, C4H10. So there are 4 carbons and 10 hydrogens. Calculate the number of moles of carbon dioxide given off when the butane is burned. So if you want to try it out on your own, you can pause the video, then you can compare with the answers that we get. Okay, so basically what you do, you write the moles. So this is the solution. So first of all, you have to check if it's balanced. So here there are 2 nitrogens. So in this case is 2 times 1, it's 2. Then here there are 6. So it's 3 times 2, it's 6. Then this one, 2 times 3, it's 6. So it's balanced. So you already know that it's balanced. So we want to form nitrogen S2 hydrogen. So here there's 1, S2, 3. So this is the molar ratio. Then for the other one, it's ammonia, NH3 to hydrogen. So you take a 2 from here, S2, 3. So this is the mole ratio. So if you came up with this, then you did it correctly. Then for the other one, you form a reaction. You know that if a cane of butane contains 1.2 moles of butane, calculate the number of moles of carbon dioxide given off when it burns. So we know that when hydrocarbons, when they burn, they need oxygen. So when they burn, they form carbon dioxide and water. So basically, this is the balanced equations of how you. So basically, when you write it, it will be C410 H10 plus oxygen to form carbon dioxide and water, like that. Okay, let me. Okay, I just want to move it, yeah, so that at least it's fine. So basically, if you check this side, you see there are 4 carbons here, but this side there are 2. There is 1, I mean. So basically, what you do, you put a 4 here, so the carbon is balanced. So you move on to the hydrogen. Hydrogen, there are 10, but this side there are 2. So okay, let me create a space here. Okay, so here you put a 5. This is the process of balancing. So here there are 10, but now the oxygens. At this side there are 2, but at this side we now have 4 times 2, that is 8. Then plus these ones, you get 13 oxygen. Eight plus 5 equals 13. It goes to 13. So this is how it is. So this is how you arrive to the. So as you can see, we had, I think when I was typing this, I think I made an error here. So as you can see here, it's supposed to be a 4. Here, supposed to be a 4. So this is good because we have already. So when you are comparing now, butane against, because remember you want to calculate the number of moles in carbon dioxide. So this is your carbon dioxide. So it's 1s2, which means 1 butane produces 4 moles of, 1 mole of butane produces 4 moles of carbon dioxide. So, but we know that we are using 1.2 moles in our, that is what we have. So 1.2 moles, it will form. Remember, the reason why we are not worried about the amount of oxygen, because it's reacting in the air, so the amount of oxygen in the air is unlimited, as opposed to the butane. So we are only worried about the relationship between butane and carbon dioxide. So we know that there will be, since 1 mole gives 4, then 1.2 gives slightly more carbon dioxide. So when you use the conversion, it will be 1.2 over 1 times 4. So basically you get 4.8 moles of carbon dioxide given off. So remember, the question was saying calculate the number of moles. So there is no need for you to further. If they required you to convert it to grams, then you have to change the moles into grams to find the amount of carbon dioxide in grams. But in this case, the question was just simple and asking you to calculate the moles. So this is how we use the molar ratios. Mole mass problems. 1.5 mole of potassium chlorate, chlorate decomposes. How many grams of oxygen will be produced? So usually when they give you these type of questions, they provide the equation so that you don't have to crack. So if you go to the periodic table, these are the mass numbers that will be given. So remember, when it's like this, it's already a balanced one. Say 2 potassium, 2 potassium, 2 chlorine is 2 chlorine, then 2 times 3, 6 oxygen. So 2 times 3, 6 oxygen. So it's a balanced reaction. So if you can try it out and find out how many grams of oxygen will be produced. So let's move on to the question. So there are 3 steps to follow. So use mole mass ratios. So in basically we are comparing, since we are already given the moles here, we compare this one and this one. So it will be it S2 oxygen. So it's 2 S2 3. So get the answer in moles and then convert into mass. So if you are given mass in the problem, you need to convert this to moles. So basically, if this figure was in grams, it means you have to first find the moles, because these equations, they work with moles. This is molar, that's why we call them mole ratios. It's not mass ratios, it's mole ratios. So if you use mass or grams, kgs, you'll get the wrong answer. So in this case, you can see it's 2s/3, we've got 1.5, so it means we will get slightly less than 3 moles. So it will be, since it's less, it will be 1.5 over 2 times 3. Then you get this answer. So these are the moles. But you want to find the mass. So this is the formula you should also remember. This is number of moles, n number of moles. This is the mass in grams, and this is the molecular mass, which means of the compound. Molecular mass. So basically the molecular mass, so in this case to convert the moles into grams, it's n, like this, which is, we want to find the grams, so we just change the assembly formula. So m is equals to n r. So number of moles is 2.25. Then oxygen. So remember, oxygen is like this. So it if you go to the periodic table, it's 16.8. So remember, we are worried about this 16. So since there are 2, so it's 16 plus 16. So 2 times 16. That's where the 32 is coming from. So when you simplify it, you're supposed to get 72 grams. So this formula is very important. You should it should be part of your stoichiometry repertoire. So let's move on. So you can try this. We want to produce 2.75 moles of potassium chloride. how many grams of laureth will be required. So remember, you are using this equation. You are using this equation. So let me maybe. So just to make it easier for you, so we are saying this one. We have 2.75. That's what we want. 2.75 moles. So how many of this do we want? So remember, as you can see, this one, since it's 2, so it means it's 1:1. So it means for us to produce 2.75 moles, we will need 2.75 moles in this case. So that's how you do it. So how many grams of potassium chloride are needed? So remember, grams, remember our formula N, M over MR. So when you want grams, so it's MR like that. So it's 2.75 moles times the molecular. So we already know from the question that K is 39, chlorine is 35.55, and oxygen 16. So that's how we do it. So 39 plus 35.5 plus 16 for oxygen, but remember it's times 3 now. So when you simplify it, then you use your calculator to find the final answer. So this should be the final answer you get. So I believe everything is clear. So once you master the how to manipulate these formulas, all these stoichiometry questions will be easy. So I would advise you for you to purchase the course on our website for comprehensive practice questions and exam preparation. So let's move on to the next. Things to note. There are 4 steps involved in solving these equations. So the first step, make sure you are working with a properly balanced equation. So if the equation is not balanced, then you are in trouble. Convert grams of the substance given in the problem to moles. So remember, chemical reactions or chemical equations, the equations are in moles. The ratios between, we are looking at mole ratios. So remember, if there are grams, you have to convert them into moles using this formula. So if it's mass, you want it's MR like that. So you can imagine. So this one is easy because it's always given. You can always calculate it using your periodic table, or sometimes it's given in the question as part of the question. So 3, construct 2 ratios. So 2 ratios that come from the balanced equation. 1 from the problem and 1 from the equation. So this is basically what we were doing. If you look at this case, in this case we wanted to balance it. So 1 is from the equation, from the one given and the one that is needed. So in this case we were working with oxygen. The one was given and the other one we were looking for. So that's what we mean by 1 from the problem and 1 from the equation. So set them equal and solve for x. This is basically what we're doing. Then step 4, convert moles of the substance just solved into grams. That is if they require it in grams. But as you can see from the previous one, the first one, they wanted they wanted the number of moles, so there was no need for us to convert it into grams. So that's why this answer that we got here, it was in grams. But the other one, it wanted the answer in grams. That's why we proceeded to use this formula to find the grams. So thank you for that. We can use to percentage composition. So percentage composition, the more-to-more relationship in a chemical formula can also be used to determine the percentage composition of an element in a compound. So basically, let's say like the one we previously looked at, this compound. If you want to find the percentage of chlorine in this one, it means you'll be using the number, the total mass of this, then you divide by the, so it will be like the total mass at the bottom, then the mass of the element on the top, so you then multiply it by 100. So basically this is what they're trying to do here, to find the amount of chlorine in this compound. This is just an example. So element, percentage element, so the number of atoms in the element. So in this case of this one, we'll be saying there will be 1 chlorine, then the molar mass of the element, then chlorine, it was 35.5, then the total mass of the element. So in this case it will be potassium 39 plus 35.5. Remember, it's for the total oxygen. Then 16 times 3. So when you simplify it, it will be 35.5 over. Okay, let me just use my calculator. But this one is just, I was just trying to use it so that you can see what we are looking at. Because we just when I am doing this lecture, some of the things they just come by, so that maybe I can show you better how to do it. So 16 times 3, so I'm supposed to get 1225 times 100. So here to be percentage chlorine in this this. So when you say 35.5 divided by 122.5, I said multiplied here, so divided, then times 100. Okay, 35.5 divided by 1.225 times 100. It means there's 28.98%. So depending, so which is approximately 29%. So this is what we, so some questions will give you a compound, then they ask you to find a percentage of an element in a compound. So basically, this is how you do it, and I'm happy for that. I just want to check. Okay, we're almost done with this session. Okay. So an example, what is the percentage composition of hydrogen in water? So you can try that one out. So you just use the same formula that we used before. Then you can try it out. So you can use this formula. Okay, let me delete this so that you can see. So if you have tutorials, if you buy the tutorials on our website, we will provide these slides for you so that you can also print them out and it will be easier for you to refer. But anyway, it's fine. So I hope you have tried it out. So we go to the solution. So first you have your formula, then you input number of, so it's water, remember, So we want hydrogen percentage. So here it's percentage hydrogen in water. So for hydrogen we've got 2, then the mass is this from the periodic table, then the total number. So this is for oxygen plus the 1 for hydrogen. So when you multiply by 100, you're supposed to get this answer. So it's fairly simple and straightforward. So empirical formulas from percentage composition. The first step in the process is to understand that the percentage composition of any element is equal to the mass number that the element in exactly 100 grams of the compound. So empirical formula. So sometimes the scientists, when they want to find the chemical composition of a substance, they use these empirical formulas so that they can predict the formula of the compound. So this is basically the exercise you'll be doing. So here they just use 100 grams as a hypothetical mass of the element, so that because they know the percentages from their scientific calculations. So a compound containing only phosphorus, because this will be done from when they examine the substance and they find out there is phosphorus, there is chlorine, and is analyzed and found to be containing 22.55% phosphorus and 77.45% chlorine by mass. So basically the percentage composition is written as follows. So you say 22.5% is written in this compound. So this is how we do it. So you convert that percentage into grams. So basically 25.55% into grams. So that's how you get the 22.5. So remember, it simplifies to. So that's how we are getting here. So the compound we are assuming is this one. We are assuming that the total mass of the compound is 100 grams. Because why we are using 100 grams? Because 100 grams is easier to work with, because you know that percentage is based on a scale of 0 to 100. So when you use 100 grams as the hypothetical mass of the compound, then we make it easier for us. So we know that 22.55% converts to 22.5 grams, 22.5 grams. So this is how we come about. So thus, if we assume that we are working with a sample that is a mass of exactly 100 grams, the mass of each element present is equal to the percentage composition. So basically that's how we are calculating here. Then from these grams, you can now find the moles. Okay, let's move on. To determine the empirical formula of the compound, the mass of each of the elements is converted to moles. So now we are now converting the grams that we get. Remember, moles is M over MR. So in this case, this is how we do it now. So you'll be from your formula of phosphorus. If you go to the periodic table, you get this one. So this is from a periodic table with very high accuracy. But when you are doing it, you use the periodic table you are given. So sometimes they round it to 30.5, 30.55. as you can see, but you just use the ones you are given. So when you calculate the mass, so we know that the mass is for P, phosphorus, let me put the P here. So you'll be saying 22.5 grams divided by this one. So in some periodic table, it's 30.5. They just round it up. Then when you do that, you get something like this. Yeah, I'm just rounding up these figures. So, but basically, when you are calculating these ones, you have to use, if you round it up too early, it might affect the ratio here. So don't round it. Here I'm just because there's no space. So you'll be using these ones. So once you get the moles, you'll be knowing that it's P has got these moles against this one. But remember, we want to use it in whole numbers. So we take the smaller one and we divide into each of the numbers. So that's what we are doing here. So let me read here. However, the empirical formula is written in the simplest whole number. So that's why we are taking the smaller one and dividing it in each number ratio. Of the element, this can be achieved by dividing the smallest amount present to produce integer subscripts without changing the relevant amount of each present in the compound. So the smaller one is 0.782. So for the chlorine we divide it, then we get almost like 3. Then for this one it will be 1. So basically this is the formula of phosphorus chloride, trichloride. So basically, this is how you find using the empirical form. Because they take a substance, then they examine the type of elements that are in there, and they measure the mass, and they find out that the other one is 22.55%, which is phosphorus, and the other one is 74.75. So from there, we assume, like we are dealing with the amount of substance in the element, we are assuming it is with a mass of 100 grams. So if you can assume any other number, but now it's better to use 100 grams, but it will make your calculations easier. But if you want to make your life harder for yourself, then you can choose any other mass you want. So, limiting reactants. A balanced equation represents a situation in which a reaction proceeds to completion and all the reactants are converted into compounds. A balanced equation, so for example, represent a situation. So let's use the example A plus 2B is equal to 3C. This is just a hypothetical example. So we are saying a balanced equation represents a situation in which a reaction proceeds to completion and all the reactions are converted into products. Under non-stoichiometry condition, the reaction continues only until one of the reactants is entirely consumed. So in other words, let's say I have 3A plus 2B. It means since I need 2A and 2B to form 3C, it means that only 2A here will be used and 1A will be left. So that's what we mean. So in other words, B will be the limiting one. If there was more B, this other 1A left, it will be used. So that's what we mean, that under non-stoichiometric conditions, the reaction continues only until one of the reactants is entirely consumed. At this point, the reaction stops. So when B is finished, then the reaction stops, although there is still 1A remaining from the 2A that was used. So that's what we are basically doing. So if they say find the limiting reactant, that's how you do it. You identify the reactants that will be consumed first. In such situation, it is important to know which reaction will be consumed first, i.e., that is the limiting reactant, and how much product can be produced. So in this case, you might be also to ask to find the percentage yield. But if you are dealing with nice geometric conditions, sometimes the reaction does not reach its full potential. So when it does not reach its full potential, we talk of percentage yield. So percentage yield is the actual yield, the one which we find in the 9 stoichiometric conditions, and the theoretical one, the one which was supposed to be yielded if the theoretical conditions were first. So this is the formula for calculating. So some of the questions and practical examples will be covered on our website. If you need more extra practice and exam preparation, make sure you can visit our website, and we will make you go through your this course with ease. If you have any questions or comments, you can write them below. If you need to email us, our email is on the right. Please like this video to know that, so that we know that you are enjoying, and also subscribe to join our online community. Thank you for your time, and wish you all the best. Bye-bye.